Welcome to the first part of our cabin atmosphere module, part of the airframe course. In this lesson, we'll explore the structure and composition of Earth's atmosphere, the human body's need for oxygen, hypoxia, carbon monoxide poisoning, oxygen and pressurization systems, and much more. Let's begin with a closer look at the atmosphere itself. The atmosphere wraps around the Earth and extends more than 20 miles upward. Because air has mass and is compressible, gravity pulls more of it toward the surface. This means the lower levels of the atmosphere are much denser than the upper layers. About 78% of the atmosphere is nitrogen and 21% is oxygen. The remainder is composed of water vapor, carbon dioxide, and inert gases. Air density is essentially how tightly packed the air molecules are in a given volume. When atmospheric pressure drops, so does air density, and as temperature increases, the density decreases even further. These variations become crucial in aviation, especially when managing cabin pressure and oxygen systems. To standardize measurements, we define sea level pressure as 29.92 inches of mercury, or 14.7 psi. As altitude increases, pressure decreases. These standard conditions help us design and test aircraft systems for real-world performance. When we breathe in, the lungs expand and atmospheric pressure helps push air into tiny air sacs called alveoli. Oxygen diffuses through the alveolar membranes into the bloodstream. The heart and circulatory system then deliver oxygen to cells where it powers vital biochemical processes. The waste product, carbon dioxide, is then picked up by the blood and carried back into the lungs through blood vessels called veins. The cardiovascular system is made up of the heart, lungs, arteries, and veins. For this process to work, there must be enough oxygen, and it must be under sufficient pressure to cross the alveoli membrane and enter the blood. As altitude increases, both total and oxygen pressure decrease, making supplemental oxygen necessary. Oxygen accounts for about 21% of the total atmospheric pressure. This 21% is called the partial pressure of oxygen. At higher altitudes, the total pressure drops so low that even though the oxygen percentage remains constant, its partial pressure may be too low to support life. That's when hypoxia becomes a real danger. Hypoxia occurs when the body is deprived of adequate oxygen. As the severity increases, a person's time of useful consciousness drops. This is the period during which someone can recognize the problem and take action before losing the ability to respond. First symptoms of hypoxia, usually noticed around 10,000 feet, include rapid breathing and headache. As it worsens, symptoms can include dizziness, numb fingers, blurred vision, and drowsiness. Because symptoms are hard to self-recognize, many aircraft have pressurization alarms for early detection. Carbon monoxide is an odorless, colorless gas that results from incomplete fuel combustion. Once inhaled, it bonds with hemoglobin more effectively than oxygen, severely limiting the blood's oxygen-carrying capacity. Even a small amount of carbon monoxide over time is dangerous. Its effects are cumulative. Long-term exposure to low concentrations can be just as harmful as a short burst of high concentration. Exhaust leaks, even pinholes, can allow it to seep into the cabin. Carbon monoxide detectors are critical, especially in piston-powered aircraft. These indicators alert pilots to dangerous concentrations early enough to prevent incapacitation. This type of carbon monoxide detector consists of a tablet that changes color when exposed to carbon monoxide. Let us dive deeper into oxygen and pressurization systems. To offset the decreasing oxygen levels at high altitudes, aircraft use two main strategies: supplying supplemental oxygen and pressurizing the cabin. Above 10,000 feet, oxygen must be added to maintain safe physiological conditions. Pressurization systems simulate lower altitude environments to keep occupants safe and comfortable. Oxygen is a colorless, tasteless, and odorless gas. It's chemically reactive and supports combustion, meaning it doesn't burn on its own but can greatly intensify fire. Commercially, oxygen is extracted by liquefying air and allowing the nitrogen to boil off. It should not be used anywhere there is any fire, hot material, or petroleum products. If pure oxygen is allowed to come in contact with oil, grease, or any other petroleum product, it will combine violently and generate enough heat to ignite the material. Common sources of oxygen include gaseous oxygen stored in steel cylinders, liquid oxygen in Dewar containers, or chemically generated oxygen. A Dewar is a special type of thermos bottle used to hold extremely cold liquids. Most general aviation aircraft use steel cylinders holding gaseous oxygen at 1,800 to 2,400 psi. Liquid oxygen is a pale blue, transparent liquid that will remain in its liquid state as long as it is stored at a temperature below -181 degrees Fahrenheit. This figure shows a Dewar flask, which resembles a double wall sphere having a vacuum between the walls. The vacuum prevents heat from transferring into the inner container. Solid oxygen generators consist of chemical blocks, often sodium chlorate, encased in steel. When activated, usually by pulling a lanyard, they produce oxygen through a chemical reaction. These are common in airliners for emergency cabin depressurization. Solid oxygen candles have an almost unlimited shelf life and do not require any special storage conditions. They are relatively inexpensive and lightweight. They are ignited either electrically or by a mechanical igniter. They cannot be tested without being used. They generate heat whenever they are used. So, they must be installed so that the heat can be dissipated without damaging the aircraft structure. Mechanical oxygen separation systems use a molecular sieve that allows only oxygen to pass through. The system continuously purges nitrogen and reuses the sieve for the next cycle. This system is common in military and some advanced civil applications. Let's now take a look at oxygen systems and components. Older military aircraft often used low-pressure oxygen systems, about 450 psi, but these required large tanks and were phased out for high-pressure systems. Today, almost all gaseous oxygen is stored in green-painted high-pressure steel cylinders under a pressure between 1,800 and 2,400 psi. All cylinders approved for installation in an aircraft must be approved by the Department of Transportation. Today, all cylinders must be hydrostatically tested at 5/3 of their working pressure, typically every 5 years. Each oxygen cylinder must be marked with its identification number, manufacturing date, and all test dates. This ensures traceability and safety. Any cylinder without proper markings should be removed from service. The cylinders for either type of system must meet the same requirements and should be painted green and identified with the words "Aviators Breathing Oxygen" written in white letters on the cylinder. To prevent overpressure and high temperatures, oxygen systems include thermal relief valves. If the pressure exceeds limits, a blowout disc will rupture and release the excess gas. A missing green disc on the aircraft's exterior signals that a blowout has occurred. Oxygen regulators come in two main types, manual and automatic. The continuous flow regulator is simple but wasteful. Oxygen flows continuously, even when not inhaling. It's commonly used in light aircraft where demand is low. The manual continuous flow regulator includes two gauges, one for system pressure and another for flow rate. The flow is manually adjusted to match altitude and must be reset during climbs or descents. Simple, but requires pilot attention. This diagram shows a manual continuous flow regulator. It requires continuous adjustment relative to the altitude. The automatic continuous flow regulators automatically adjust the oxygen flow based on altitude. Once activated, they meter the correct amount of oxygen without further input. This reduces workload during flight. Demand regulators deliver oxygen only during inhalation. This regulator is fitted to a portable oxygen bottle and a full face mask. This type of system is often used aboard cargo aircraft as a smoke combat unit to allow a crew member to locate and extinguish a cargo fire. It is much more efficient than the continuous flow type. Above 25,000 feet, the rebreather mask can't keep the oxygen percentage high enough to keep the pilot safe. Aircraft that operate above 25,000 feet and up to 40,000 feet use a diluter demand oxygen system. This system uses a face-tight seal to ensure cabin air doesn't unintentionally mix into the mask. The system then automatically mixes cabin air with oxygen to maintain a safe oxygen saturation. Unlike a continuous flow system, the diluter demand mask doesn't constantly pump oxygen. Instead, it only supplies oxygen as you breathe. Since it automatically mixes oxygen and air only as you inhale, a diluter demand system generally lasts longer than continuous flow. When the supply lever of the diluter demand oxygen system is turned on, with the oxygen selection lever at normal, oxygen is allowed into the system through a pressure reducer. The oxygen then passes through the demand valve, which is controlled by the demand diaphragm. Meanwhile, the inlet air cover is open to allow cabin air into the system. The amount of cabin air is regulated by the air metering valve. The air and oxygen then mix and are supplied to the mask depending on the demand of the user. If the emergency lever is turned on, 100% oxygen is supplied to the mask. Pressure demand regulators ensure oxygen delivery at very high altitudes, above 40,000 feet. The system forces pressurized oxygen into the lungs during inhalation. The high pressure, combined with 100% oxygen, keeps the oxygen's partial pressure high enough for the lungs to absorb a safe level of O2. Since the system forces air into the lungs under pressure, one will need to force it back out during exhalation. This can be exhausting. This is a diagram of a pressure demand oxygen regulator showing the oxygen supply pressure. Let's now consider oxygen masks. Rebreather masks are used with continuous flow systems and capture exhaled air for reuse. They are a simple bag-type disposable mask used with some of the portable systems. The demand-type masks deliver oxygen only when you inhale. These are more efficient and are standard in most commercial operations. If an aircraft has an installed oxygen system, it will be one of three types: the continuous flow type, diluter demand type, or pressure demand type. In most single-engine aircraft, continuous flow systems are used. They feature an external filler port with a safety cap and restrictor orifice to prevent overfilling. Simple and effective, especially for occasional high-altitude operations. The shutoff valve on the cylinder is of the slow-opening type and requires several turns of the knob to open or close it. Some installations use a pressure-reducing valve on the cylinder. When a reducer is used, the pressure gauge must be mounted on the cylinder side of the reducer to determine the amount of oxygen in the cylinder. The typical general aviation aircraft has an installed system similar to the one shown in this diagram. Pressurized aircraft don't typically supply oxygen to passengers unless required. FAA regulations mandate that crew members wear masks above certain altitudes. High-performance aircraft use diluter or pressure demand regulators for the flight deck. Aircraft that do not require oxygen to be constantly available to passengers will have a diluter or pressure demand regulator for the flight crew. LOX systems are not common in civil aviation due to complexity and servicing difficulty. However, the military uses them extensively for weight and volume efficiency. 1 liter of LOX can produce 860 liters of gaseous oxygen. Liquid oxygen systems require specialized plumbing to handle the conversion from liquid to gas and the venting of excess pressures. Liquid oxygen is held in a spherical container, and normal operation, the buildup and vent valve is back-seated so some of the LOX can flow into the buildup coil, where it absorbs enough heat to evaporate and pressurize the system to the amount allowed by the container pressure regulator, normally 70 psi. This gaseous oxygen maintains a relatively constant pressure in the container, and supplies oxygen to the regulator. If for any reason excessive pressure should build up in the system, it will vent overboard through one of the relief valves. Chemical oxygen candles are activated in emergencies by pulling a lanyard. This triggers a chemical reaction that generates oxygen. Their simplicity and reliability make them ideal for airliner passenger masks and life rafts. Chemical oxygen candles produce oxygen by heating sodium chlorate. The sodium chlorate is converted to salt and oxygen. The shape and composition of the candle determine the oxygen flow rate. As the sodium chlorate decomposes, it produces oxygen by a chemical action. An igniter, actuated either electrically or by a spring, starts the candle burning. These have a long shelf life and make them ideal for emergency oxygen use during pressurization loss. The emergency oxygen systems for pressurized aircraft have the oxygen generators mounted on either the overhead rack, in seat backs, or bulkhead panels. Once a chemical oxygen candle is ignited, it cannot be shut off. It must burn till exhausted. Pulling a lanyard on some chemical oxygen candles removes the safety pin to allow the spring to actuate the igniter. Aircraft that do not require oxygen to be constantly available to passengers will have a diluter or pressure demand regulator for the flight crew. Oxygen leaks are detected using a non-oily soap solution. Apply it to fittings and valves. If bubbles appear, there's a leak. Repair any leakage immediately before placing the system back in service. Before draining, isolate or remove the cylinder. Always drain in a ventilated area and follow procedures to bleed off pressure safely. Most systems also require purging after draining to remove air and moisture. Oxygen filling is typically done using an oxygen cart with 6 large cylinders. The manifold allows for sequential use, reducing waste. Always maintain a residual pressure in each tank to prevent contamination. This consists of a battery of oxygen bottles hooked to a common service manifold. Sometimes a nitrogen bottle is on the same cart but with different hose fittings to prevent inadvertently interchanging the two systems. No oxygen system should be allowed to become completely empty. When there is no pressure inside the cylinder, air can enter, and most air contains water vapor. The design of the hose manifold for oxygen servicing allows each bottle to be connected in turn to the receiving system. This temperature-compensated chart ensures the correct fill pressure based on ambient temperature. Overfilling or underfilling can result in system failures or insufficient oxygen delivery. If the system has been opened, purge it to eliminate moisture or contaminants. For continuous flow systems, connect masks to each outlet and run oxygen through the system for 10 minutes. Servicing lock systems involves highly cryogenic liquids, so protective gloves and goggles are a must. The LOX cart connects similarly to gaseous systems, but must be handled cautiously due to frostbite and explosion hazards. Masks and hoses must be checked regularly for damage, cracks, or contamination. Disposable masks are discarded after use. Permanent masks are assigned to individual crew members and stored away from oil, dust, or moisture. Before replacing any oxygen system component, it must be inspected, cleaned, and thoroughly degreased. Approved solvents like acetone or stabilized trichloroethylene are used for flushing, followed by dry air or nitrogen. Ground all equipment and remove flammable materials from the area. No smoking or open flames within 50 feet. Oxygen cylinders must be stored upright in dry, shaded, and well-ventilated areas, away from oils, grease, and direct sunlight. Let us now shift focus to pressurization. With piston engines, pressurization often requires superchargers or supplemental oxygen. During World War II, The development of pressurized cabins allowed bombers to fly at higher altitudes with greater comfort and safety. When the jet transport airplane began to fly in the early 50s, the large pressure differential required for the altitudes they flew created metal fatigue. Metal fatigue, caused by the repeated pressurization and depressurization cycles, caused several disastrous accidents. A pressurized aircraft maintains a cabin pressure significantly higher than ambient pressure at altitude. This creates a differential, which must be managed carefully to avoid exceeding the aircraft's structural limits. To control cabin pressure, outflow valves adjust the amount of air exiting the cabin. Isobaric mode maintains a constant cabin altitude, while differential mode maintains a set pressure difference between inside and outside. The source of air to pressurize an aircraft varies mainly with engine type. Reciprocating aircraft have pressurization sources different from those of turbine-powered aircraft. Note that the compression of air raises its temperature. A means for keeping pressurization air cool enough is built into most pressurization systems. It may be in the form of a heat exchanger, using cold ambient air to modify the temperature of the air from the pressurization source. There are three typical sources of air used to pressurize reciprocating aircraft: supercharger, turbocharger, and engine-driven compressor. Superchargers and turbochargers are installed on reciprocating engines to permit better performance at high altitude by increasing the quantity and pressure of the air in the induction system. Some of the air produced by each of these can be routed into the cabin to pressurize it. The main principle of operation of a turbine engine involves the compression of large amounts of air to be mixed with fuel and burned. Bleed air from the compressor section of the engine is relatively free of contaminants. As such, it is a great source of air for cabin pressurization. The main principle of operation of a turbine engine involves the compression of large amounts of air to be mixed with fuel and burned. Bleed air from the compressor section of the engine is relatively free of contaminants. As such, it is a great source of air for cabin pressurization. Smaller turbine aircraft, or sections of a large aircraft, may make use of a jet pump flow multiplier. With this device, bleed air is tapped off of the turbine engine's compressor section. It is ejected into a Venturi jet pump mounted in air ducting that has one end open to the ambient air and the other end directed into the compartment to be pressurized. Cabin pressure is managed by regulating airflow into and out of the cabin. Controlled leakage occurs through outflow valves. Uncontrolled leakage escapes around seals and other minor gaps. Cockpit indicators include cabin altitude, rate of climb, and differential pressure. These help the pilot maintain passenger comfort and structural safety. The control panel allows adjustment of cabin settings during flight. This diagram shows the cockpit control panel for a typical transport category aircraft pressurization system. Controlling cabin pressurization is accomplished through regulating the amount of air that flows out of the cabin. A cabin outflow valve opens, closes, or modulates to establish the amount of air pressure maintained in the cabin. Some outflow valves contain the pressure regulating and the valve mechanism in a single unit. They operate pneumatically in response to the settings on the cockpit pressurization panel that influence the balance between cabin and ambient air pressure. The outflow valve maintains a set altitude until the pressure differential with outside air approaches the structural limit of the aircraft. It then maintains a differential with the outside pressure. Aircraft pressurization systems incorporate safety features to limit human and structural damage should the system malfunction or become inoperative. One of such safety features is the cabin air safety valve. A cabin air safety valve is a pressure relief valve set to open at a predetermined pressure differential. It allows air to flow from the cabin to prevent internal pressure from exceeding design limitations. A negative pressure relief valve is also included on pressurized aircraft to ensure that air pressure outside the aircraft does not exceed cabin air pressure. The spring-loaded relief valve opens inward to allow ambient air to enter the cabin when this situation arises. This diagram shows a typical pressurization control panel in the cockpit. Cabin air is a mix of bleed air and cooled air from the air conditioning system. A check valve ensures air doesn't leak backward if the compressor fails. This system provides fresh, tempered air throughout the cabin. The pressurized air is distributed to the side wall or overhead vents in the cabin. The cabin air is then drawn back into the conditioned air manifold to recirculating fans, mixed with new incoming air, and then redistributed to the aircraft cabin. Troubleshooting involves checking cabin leaks, valve operation, and system response to altitude changes. Improper pressurization can result in discomfort or even danger at high altitudes, so periodic checks are essential. That concludes Part 1 of our cabin atmosphere module. We've explored everything from oxygen generation and delivery to pressurization systems and safety precautions. Stay tuned for Part 2, where we'll dive deeper into air conditioning and environmental control systems. Thanks for joining me, and I'll see you in the next lesson.